see? You see the syllabus?
Right now, I see driving down the highway.
Okay, it should change to PJ in a sec.
Driving down the highway.
Okay, now I see PJ.
There's still a pretty significant delay there, isn't there?
I can see it right now, yes.
So that much delay. I was there a long time ago. That's strange. Okay, so today is lithium-ion battery lecture 6. So this is probably the first lecture where we will actually concentrate on lithium-ion battery technology. So far, we've been discussing, introducing the background. So we have introduced some background, not enough, because background itself can be a semester course, right? So at some point we have to say, okay, let's move on with the technology. So today is the first lecture totally dedicated to lithium-ion batteries. Okay, so why lithium? Why bother with lithium? Okay, so why Li? And the many reasons. One is that lithium is very electropositive. What that means is lithium loves to give up its electrons. Or each lithium atom has one electron, give up its electron. So this reaction would be Li giving you Li plus electron. So lithium loves to go in that direction. And it's got the highest, or I should say extreme voltage or potential of all metals. So highest or lowest. For example, if you look at the galvanic series, if gold is here, silver is below it, copper is below it, zinc is here, lithium is here, aluminum is probably somewhere over here. So lithium is at the opposite extreme of gold. So that gives it an advantage. So LIB batteries, lithium ion batteries, they can give about 4 volt output, maybe a little less. So that's good output voltage. Lithium ion battery has low maintenance. And it's safe from the point of view that there's no lead in the battery, in the cell. So those are some of the reasons for using lithium. So now let's just draw the lithium ion battery structure. So just a basic structure of the battery in its simplest form would be, you need a negative electrode, you need a positive electrode. So the negative electrode is graphite. So the graphite needs to be backed up with a current collector. So the current collector that is copper. So before I forget, this structure I'm describing came from Sony Corporation in the 1980s. So there are many different structures. I'm just describing the one by Sony. So Sony did amazing work in this area in the 1980s. They have a lot of the inventions in this technology. Okay, so what about the positive electrode? So positive electrode has lithium cobalt oxide. And this needs to be backed up by a current collector, and this current collector is made of aluminum. Okay, what about the electrolyte? So the electrolyte is the solvent is ethylene. One solvent is ethylene carbonate. There are others. So this is a liquid. Ethylene carbonate is a liquid. And to that, you add a salt, which is LiPF6 salt. And there's one more component, and that is, I'll draw it over here. I'll draw it like this. This is a separator. And the separator is because we're squeezing all these together into, like, let's say, into a roll. So we stack all these and roll them up. So you actually need two separators, one over here and one over here, because you're rolling it. If you only had one, then there's short circuit, right? So just think about, you have a positive and negative foil, you're rolling them, you do need two separators, right? Instead of one. Now the separator is a polymeric material. It could be polypropylene, it could be polyethylene. So in the simplest form, this is the structure of the battery. And like I said, it can be in a roll form like this. And you have two things sticking out, the positive electrode and the negative electrode. So when it comes to battery technology, we don't talk about anode and cathode. We talk about negative and positive electrodes, and they're clearly marked on the battery. Okay, so during charging, okay, so when you assemble the battery fresh, there's no lithium here. There's lithium ions in the salt, in the electrolyte, there's lithium in the lithium cobalt oxide. So as assembled, there is no lithium ions on this. Oh, before I forget, water is bad news. Water is no good for lithium-ion batteries because lithium plus water will give you hydrogen gas. Just like if you took sodium, you can try this at home in your garage. Sodium plus water will give you hydrogen gas. It'll be a very violent reaction. So don't try that. So we have an organic, this is an organic solvent. And we want to make sure this organic solvent doesn't react with these materials in this structure. That's important. Okay, so during charging, since the freshly made structure has no lithium ions, so when we charge, lithium ions move in this direction and they fill up as much as possible this graphite. So this is during charging. And we'll go into some more details on this. During discharging, so this is discharging. Lithium ions move in that direction. So during charging, the graphite gets filled with lithium. During discharging, the lithium moves to the positive electrode. So that's the basic structure. What else have we left out? I think we covered the basics here. Oh, one more thing, just to remind you that the electrolyte is an insulator. So this region, electrolyte, is an electrical, actually I should say it's electronic non-conductor or electronic insulator. It's an ionic conductor. So it only lets ions go through, electrons can't go through. So electrons have to go through the external circuit. So electrons will go in this direction during discharging. So that's the flow of electrons. But the electrons don't flow inside this. The lithium ions flow inside the electrolyte. Okay. So here we are showing graphite, but why not use lithium itself? Why not use lithium electrodes? People have tried that. That's the first thing you would try, right? So why not lithium electrodes? So why not Li electrode for the negative side, right? And the main reason is that lithium electrode, and this is a very important reason, will grow dendrites. So what happens is that suppose I have a lithium electrode like this. I'm just drawing, so this is a foil, I'm just drawing the cross section, right? When we are charging the electrode with lithium ions, lithium metal can grow like this. And it can short circuit to the positive electrode. So then you have a safety issue, right? That's the main reason. So what does graphite do that lithium cannot do? Graphite. Why is it great? So why is graphite so great? The reason is the graphite is in sheet form, especially well-made graphite with high graphite structure. It's in this sheet form, and the lithium ions, they can have intercalation. This big word, what that means is lithium ions can come and sort of fill this space. So notice this is 3D filling. In other words, if this was the electrode, then all of it, even inside it, can be filled with lithium ions. Whereas in the case of lithium metal, it's only on the surface. So notice that the surface area is increased. So the capacity for energy storage is increased because you can fill this whole space with lithium ions. So this is a very important thing, intercalation. The same intercalation happens for the lithium cobalt oxide. Here also, within the structure, the lithium ion atoms can fill this space. So intercalation is both for the negative electrode, which is graphite, and for the positive electrode, which is lithium cobalt oxide. So this is a big important message, that the graphite electrode, which is negative, and the lithium cobalt oxide electrode, which is positive, can have intercalation. Now here, I'm going to remind you, I'm only talking about the Sony version of LIB, lithium-ion battery. There are many different versions, many different oxides, and many different forms of graphite. I'll only talk about one form of graphite. Okay, so let's discuss just for a few minutes what happens at the negative electrode, which is graphite. So we have lithium ions plus C6 plus electrons giving you lithium. So this is during charging. So this is at the negative electrode. And just to keep it generalized, okay, I have to write over C6. So the reason I write C6 is for every 6 carbon atoms, I can have 1 lithium ion. So if I have 12 carbon atoms, I can have 2 lithium ions that can go into the structure. To keep it generalized, I can put X over here, I can put X here, and I can put X over here. So this is during charging. So this is a charging direction, and I can write down this is during discharging in that direction. At the positive electrode, so this would be lithium cobalt oxide. What happens? Here, okay, let me just draw charging first. So we have lithium cobalt oxide. During charging, it'll give you LiCoO2. So I'll put 1 minus X over here of lithium plus X Li plus. So this is during charging. So I'll write charging over here, and this is during discharging. So now, so here we can have a maximum of 1 lithium ion for 6 carbon ions. What about over here? So the reason we put 1 minus X and X and all that is because here X cannot be greater than 0.5. In other words, we can't have, let's say, 0.6 over here. So let's see, let me put it this way. X greater than 6 is not allowed because X less than 5 is not allowed, because then there will be too many lithium atoms in LiCoO2, and this oxide will become unstable and the reaction will be irreversible. So you want to be able to go back and forth here. So you can have only, you can remove only so many lithium atoms from the lithium cobalt oxide. If you remove too many, then the structure becomes unstable. So there's a limit to how many of these lithium ions can go from the oxide to the negative electrode. So did I do this right? So I want to keep this 1 minus X high. Yes, so I'm limiting the value of X to less than half. That's correct, yeah. So that's important. So now let's discuss the charging and discharging behavior. So I can go over here. So charging, discharging curves. Okay, so this is an important thing to show. So on the vertical axis, I have potential. So this is potential of the electrode. And potential has to be measured with respect to something, and we use a reference electrode, that is lithium electrode. So that's a reference electrode. So if you have a liquid and I put a piece of metal or graphite or electrode in this liquid, and I want to measure the potential of the liquid, it has to be with reference to something, and that something is in electrochemistry a reference electrode. So generally, for aqueous electrochemistry, we use hydrogen reference electrode, but in this lithium-ion battery, since we're not allowed water, we're using lithium itself as a reference electrode, lithium metal. So if and on the horizontal axis, I'll be plotting a couple of things. In this case, I'm plotting X, which is X in LiXC6. So I'm looking at charging the negative electrode with lithium ions. So X increases from here to there, right? So X goes from 0 to, let's say, 1. So 0 meaning there are no lithium atoms in the negative graphite electrode. 1 means it's fully populated. So for every 6 carbon atoms, you have 1 lithium atom. So what does this profile look like? So let's say this is 0 volts. Let's say this is 4 volts. So the curves will look during charging. You'll have many plateaus like this, maybe one more like that. This is during charging. So for charging, I'll just say CH. During discharging, it'll be like this. So this is discharging. So why do we have these plateaus? So these plateaus are because if I look at the graphite structure, we have these layers of graphite, and so we have one plateau when we have these lithium atoms on, let's say, every third layer. We might have this plateau, and then as we populate more lithium ions, now there might be every second layer. So as we move forward, more and more layers get populated. So each one has a different potential. So notice that as we populate the negative electrode with lithium ions, its potential keeps on decreasing, which is a good thing. So what about the positive electrode, which is lithium cobalt oxide? So let's look at that one. I think I'll use a different color for that. So let me try red for that, or blue. Okay, so now what we're doing is we're looking at the charging discharging curve for oxide. So that curve will be like this. So this is during charging, and this is during discharging. Now, but in this case, we have to have another X. So for this, the X would be, I'll use this space over here. I'll draw an axis in blue. So this X would be from about 1 to 0.5, and this X is X in LiXCO2. So notice I mentioned that we cannot deplete the lithium cobalt oxide too much. We can't go beyond 0.5. So this is a range. So notice over here that as we charge the battery, so let's look at the charging. So as we charge, this is the voltage of the battery, of the lithium ion battery. So as we charge further, the voltage of the lithium ion battery increases. And as we discharge, I can draw that in red for discharge, the battery voltage decreases. Let me draw it over here. So this is the LIB voltage during discharge. So the voltage of the battery is the voltage of the positive electrode with reference to lithium ion reference electrode, and the voltage of the negative electrode This one, again, is a reference to lithium-ion reference electrode. And then we go to look at the difference between the two. That gives us the battery voltage. So we have this half cell and that half cell, and combined, we get the voltage of the battery. And again, during this time, during the charging, in the negative electrode, we are populating the lithium ions in the electrode, and during the charging also, basically we're moving lithium ions from the positive electrode to the negative electrode during charging, and the reverse during discharging. Okay, so now I want to talk about the battery capacity. So we'll talk about battery capacity, battery energy capacity. So energy let's say capacity. To be more specific, today I'll talk about maximum theoretical specific energy. So what is max? And for short, we'll say MTSE. So this is the first time we're looking at energy capacity. So let's take an example of lithium itself, lithium metal. So lithium metal has this reaction, right? And just to make it more general, let me call it metal M, which has N plus electrons. So it needs N electrons to become M. So this is a reduction reaction. So this is what we call a reduction reaction in electrochemistry. So we want to look at the maximum theoretical specific energy. In other words, we want to know, so what this empty SC means, what is the energy in terms of watt hours per kilogram. If I have 1 kilogram of lithium metal and I'm using that as an electrode, how many watt hours per kilogram can I have? And this is theoretical. In theory, in practice, it are less. But what is that maximum we can have? So let's calculate that. So we're doing a theoretical calculation. So to reduce, so we're doing a reduction reaction. So to reduce 1 mole of metal M, we need NF coulombs charge. So F is Faraday. So F is Faraday. And I think we did this before. And 1 Faraday is 96500 coulombs. So if I'm given 1 mole of a metal M, and I'm saying I want this in a completely reduced form, meaning this reaction should go that way to the extent of 1 mole, I need NF coulombs. Okay, so how many grams in a coulomb? So we have, okay, so before I go there, let's say the potential across that electrode is E. So potential is equal to E. So what am I doing? I'm taking NF coulombs and I'm pushing them through potential E. So let me just draw over here. So let's say the potential is E, and I'm taking NF coulombs from here to there. So if I move this much charge through this potential, the energy is equal to the potential times the charge. So that's how much energy it takes. So in other words, to create 1 mole of metal M from its ionic form will take ENF amount of joules, So that's for 1 mole. So now for 1 gram, so energy per gram, what do? I divide that by the molecular weight. So this gives me joules per gram. And I can say I'm interested in kilograms, so I can put K on the top and the bottom. So now this gives me so many kilojoules. Okay, so I have to change this also. So I make this into kg. So that many energy per kg. So this is our maximum theoretical specific energy. So for 1 kg of lithium, I need so much energy, and that's given by this. And now this kilojoules, I'm going to convert to watt hours. So just as sidebar, 1 kilojoule is equal to 1 over 3.6 watt hour. So this calculation you can do on your own. So I can replace kilojoules by watt hour. So I can say NFE over M. I just rearrange the terms. I'm replacing kilojoules by watt hour. I can say watt hour by kilogram. So now we know the value of F. F is 96500. So I can say this is equal to NE over M, and I can say 96500 by 3.6. That gives me 26806 NE over M watt hour kilogram. So this maximum theoretical specific energy is equal to 26806 NE over M. So now for lithium, we know what the value of M is, right? So I'm going to go on this side now. So for lithium, we know the value of M. So we are still on our lithium kick. So M is equal to, let me flip over to the next page, 6.94. So maximum theoretical specific energy for lithium is 26806 over 6.94, and N is equal to 1, so E. So N was going in the numerator and M is the denominator. So this comes to 3863 E watt hour per kilogram. So that's the maximum energy you can get from 1 kilogram of lithium. But lithium, we know is no good. So we can't use lithium because lithium, as we discussed, grows dendrites, and that's the main thing. But also, lithium reacts with organic materials. And also lithium has a low melting point, and lithium will deposit everywhere. So lots of reasons we can't use lithium. So what about graphite? So since we can't use lithium, let's go for graphite. What about graphite's MTSE? So the graphite reaction is 6 carbon, and we're writing the reduction reaction, plus lithium plus electrons gives you LiC6. So this is the reduction reaction for graphite. So in this case, our equation that we've been using, the MTSE, the maximum theoretical specific energy, is 26806 times N times E over W, right? So N is equal to 1. See, this is 1 over here. So we say 26806, 1E. What about W? So the molecular weight for carbon is 12, so we have 6 carbons. So multiply by 12, and we get 372 watt-hour per kilogram. So compare this with that, it's a lot less, right? So lithium would have much more specific energy, but we can't use it now. So next, let's look at the positive electrode. What about the positive electrode? There's a question on the screen? Oh, okay. Okay, let's see. Do the lithium ions populate a layer completely before populating the next layer, or do they distribute themselves according to some kind of bell curve? I don't know. I'm not sure how lithium ions would populate the graphite, but from what I've read, one of the papers says they go to the third layer. Every third layer is populated, and then every second layer, every layer. So that's the trend. So I don't have a good answer for that question. Thanks, Brandon. Okay, so the next one would be the positive electrode. So I think I can rub this page. Okay, so now we're dealing with the positive electrode. For that, let me write the reduction reaction. So I start with 0.5 CO2, and I combine that with half Li plus half electron. I get LiCO6, right? So for this reaction, we know that MTSE will be equal to 26806 times N times E over M. So we get 26806. In this case, N is equal to 0.5. We have E, and then M would be the lithium ion molecular weight, which would be 0.5 times, let's say, 6.9, plus for the cobalt would be about 59, plus we have 2 oxygen, 2 times 16, plus, let's say, half lithium. Actually, I can stop there. And the answer would be 137 watt-hours per kilogram. So you see that the positive electrode is limiting the amount of energy stored, because the graphite can store 372 per kilogram, and the positive electrode is storing 137. So So if we have to do an improvement, we would improve the capacity of the positive electrode by maybe using a different oxide. So this oxide, the lithium cobalt oxide, was discovered by Professor Goodenough. Not hard to forget, right? By just Professor, if his first name was Just, that would be great. Professor Just Goodenough. I don't know what his first name is, but he worked in UK, and then later on, I think he couldn't stand the climate. He came to UT Austin. I think he's probably still there. He's still working on oxides. So the novelty of this lithium cobalt oxide and different oxides is that they can store the lithium ions, and they have intercalation. And when you store these ions, the material expands, and when the ions are given off, the material contracts. So there's expansion and contraction. So that has to be taken into consideration. Okay, so back to the charging-discharging curve. So this curve I've drawn for well-graphitized graphite. So how do you make graphite? So graphite, you take carbon, it could be in the amorphous form, and then you heat it up to a very high temperature, like 2500 degrees centigrade. So the amorphous carbon will become graphitic. So here, this curve I've shown is for a well graphitized, let's say, carbon. So this has got good layered structure. So we have graphene layers, and in between these layers, the lithium ions can intercalate. Now, if you had a not so good or amorphous, let's take amorphous carbon, this curve will be a lot different. So this curve will probably, for carbon, the curves would be like this. So this would be during discharge, and this would be during charge. So now you see the voltage that the battery can have decreases. So this is amorphous carbon. And to go from amorphous carbon to well graphitized carbon, you need to heat to greater than 2400 degrees centigrade. So you get this well-formed graphite. And the reason you have this hysteresis, one factor is mechanical stresses. When you go from charge to discharge and back, so you have mechanical stresses you have to overcome. So basically, you want as perfect a graphite as you can get. And you can get that by heating up to more than 240 degrees. So what is the practical MTSC, maximum theoretical specific energy of well graphitized carbon? It's about 300 to 350 E, and compare that with 372 that we calculated. It's pretty good. So graphite can get pretty close to its theoretical value. Okay, this I should just say specific energy. This is not maximum. So specific energy for graphite practically would be in this range, whereas the maximum theoretical specific energy is 372 that we calculated before. Okay, so a little bit more on the construction, on the components. So the positive electrode, we have just said it's a lithium cobalt oxide, but it's more than that, right? So let's talk about the positive electrode, the lithium cobalt oxide. So to make the electrode, we talked about that you need a current collector. So the current collector is made of aluminum. So aluminum current collector. And so you have this lithium cobalt oxide. You also need a binder. So you need a binder. And the binder used is PVDF, whatever that means, some polyvinyl. So let me write it down. For us non-chemists, it doesn't mean anything, but it's good to sound smart. So we'll write the term down. Polyvinylidene fluoride. And for the real chemists, I'll just draw the structure. So I'm treading on unknown grounds. Don't ask me what this means, but this is a binder. And this binder, I think, also needs a solvent. Don't ask me why. So the solvent is NMP. So somehow we have a binder and a solvent, and they all combine together with this lithium cobalt oxide, and it's coated on top of the aluminum. So this is LiCoO2 plus the binder, which is PVDF, plus the solvent NMP. So this concoction, and these dimensions are very, very small. They're like microns, I think. I don't recall the dimensions, but it's extremely thin. It has to be thin because you're rolling this whole thing into a roll. So if it is thick, the stresses would be too high, right? So I won't bore you with all the properties that the binder should have. It should be inert material. It should adhere to the electrode, withstand high voltage, have high melting point, low swelling, good ionic conduction, good electronic conduction. So it needs all this bunch of properties. Okay, we already talked about intercalation, and we talked about that this lithium content, this X lithium, has to be kept greater than 0.5, otherwise the material becomes unstable. So you can only discharge to a certain extent. Oh, so notice that there are no plateaus I've shown. Like I showed plateaus for the graphite, I'm not showing those for the lithium cobalt oxide. But if you look at the textbooks, there are oxides which do have plateaus. But for some reason, for lithium cobalt oxide, they don't show any plateaus, Okay, I think I'm on my last page, and I have 5 minutes left. So last thing left is, a couple of things. The electrolyte. The electrolyte is, where should I go for the electrolyte? Okay, this is a good spot for the electrolyte. For the longest time, the electrolyte confused me. Because I'm not a chemist. So they say electrolyte can be propylene carbonate. So as a non-chemist, when I think of propylene carbonate, I think, oh my God, this is solid. But this is a liquid. And it has to have good dielectric properties, good wide liquid range, and it should not support. Okay, so the problem with this propylene carbonate is that lithium dendrites can grow in this with this propylene carbonate. And so if we have ethylene carbonate, which is also liquid, don't ask me why. This is good because it does not support, or there's less formation of lithium dendrites, whereas propylene carbonate would support this dendritic formation. And there's another very important thing going on, and that is ethylene carbonate forms solid electrolyte interface. So this is another important thing, SEI. So in the early portion of the lecture I mentioned, we're dealing with Sony. So what Sony learned and Sony's inventions. So what Sony learned was that when you have the graphite electrode, so graphite reacts with graphite reacts with some of these carbonates, and it makes the carbonate unstable. So makes the electrolyte unstable. But with this ethylene carbonate, there is a reaction that happens, and lo and behold, it forms a film on top of the graphite. And this is the solid electrolyte interface that forms. And amazingly, don't ask me how, the lithium ions can travel through this interface. So lithium ions have no issue going through the interface. And this is, so basically it can keep it keeps the electrolyte away from the graphite, but the lithium ions can travel through the solid electrolyte interface. So this was, I think, a discovery made by Sony. So Sony made many discoveries. So Sony was the one that said we can use graphite electrodes. So this lithium cobalt oxide is an invention of Professor Goodenough, but and Sony took that and they came up with the graphite negative electrode. They came up with electrolyte, and they discovered the solid electrolyte interface. And another big thing they discovered was the chemistry of the separator. So the separator is the one that separates the positive electrode from the negative electrode. And one reason that they could do that and other people couldn't do it is because Sony had this polymer chemist who had spent his life on membranes for loudspeakers. So Sony had forced him to work on loudspeakers for many years. So when he transferred to the LIB effort, he brought that technology, and for the separator, he came up with the polypropylene and polyethylene. So polypropylene, polyethylene, and he could make this polypropylene, polyethylene, so it had micropores, through which the electrolyte could go through, and the dendrites not allowed to go through. And also another big deal was, in case the dendrite went through, and let's say there was current crowding and this region became hot. So then this would melt and form an impervious membrane. So wherever let's say there was a breakdown of there was short circuiting between the two electrodes, for whatever reason, because of dendritic growth or something else, the membrane, this separator would get hot and the micropores would collapse and would become impervious membrane. So I think there's a term they use for that. I can't find it right now. Oh, yeah, thermal shutdown. So they call this thermal shutdown. So that was another discovery made by Sony. So on that note, I'll call it a day. So I'll see you in 2 weeks. Thanks, guys. Was there another question? No, there's no more questions. Okie doke. Thank you, guys.